Hello everyone, welcome to this ninth lecture in the NPTEL course on Riemannian geometry. So last time, if you remember, we discussed a few examples of Riemannian manifolds. So the aim of today's lecture is to talk about isometries, and as an example of an isometry, I will show that three of the Riemannian manifolds that we talked about last lecture are actually all isometric. Okay, so let me remind you of what those three Riemannian manifolds were. So the first one is the Poincare ball. So as a manifold, it's basically just the open ball of radius r sitting inside Rn, and the metric that you define on it is basically just a conformal rescaling of the Euclidean metric. Right, so you take the Euclidean metric and you multiply that by a positive function, you get another Riemannian metric on this open subset of Rn. That's called the Poincare ball metric. Okay, and one thing to notice is that if you look at the denominator, that blows up as x approaches the boundary. Okay, so the metric becomes really large as you approach the boundary, and one effect of this is that if you take curves that just straight line paths passing through the origin that approach the boundary, in this new Riemannian metric the lengths of those paths become really long, so that it's impossible to reach the boundary in finite time. Okay, if you reparameterize so that your curve has unit speed in this new Riemannian metric, it's impossible to reach the boundary in finite time. Alright, so the second example that we introduced was the Poincare half space. So that's again, as a manifold, it's just an open subset of Rn, namely the upper half space. So in 2 dimensions, for instance, this would be the picture, and then again the metric that you define is a conformal rescaling. So you just multiply the Euclidean metric by this factor, and again if you notice that as xn approaches 0, so as you approach the boundary of this half space, the metric again blows up. Okay, then the third and the last example that I introduced in the previous lecture was that of a hyperbolic metric. So this is slightly more involved. It's not as straightforward as just taking some open set in Rn and defining a conformal rescaling. So what you do is you start with a quadratic form, which we denoted by Q. So this is essentially, this is a quadratic form on Rn plus 1, and you basically, it's a quadratic form of signature n comma 1. So the first n terms are all positive, the first n eigenvalues, and then you have a negative eigenvalue. So explicitly it's given simply by this formula, and then you define you consider the hyperboloid, which is basically the set of all vectors in Rn plus 1, so that the quadratic form takes the value negative r squared. Okay, so the picture here will be something like this. Okay, it will be a hyperboloid. Then you take any point P on the hyperboloid and you look at the tangent space of that point. That tangent space is precisely given by the orthogonal complement of the vector, of the position vector of this point P. Okay, and of course the orthogonal complement is taken with respect to this new quadratic form of signature n comma 1. And then we saw that by Sylvester's law of inertia, we saw that if you restrict the quadratic form to this tangent space, to this orthogonal complement, it will give you a positive definite symmetric inner product, right. So that is defined to be the hyperbolic metric on this hyperboloid. Okay. Alright, so at the end of the previous lecture I discussed all these examples. So in today's lecture, as I said, we want to talk about isometries. Right. Okay, so here's a definition So let Mg and Nh be n dimensional So whenever I write this little power, this basically represents the dimension. So this is the dimension of the manifolds. Okay, so that's a standard notation that is used. So let Mn and Mg and Nh be Riemannian manifolds of dimension n. Okay, then a local isometry is a smooth map F from n to n such that 1 F is a local diffure okay so by the inverse function theorem this is equivalent to the statement that if you look at the derivative map this is an isomorphism for all points P. Okay, right. So we firstly need F to be a local diffeomorphism, and then I want G to be precisely given by F star of H by the pullback metric. So the metric on M is simply the pullback of the metric on N. So this is the isometry part of the definition. Okay, so an equivalent way, I mean that is the definition of what the pullback metric is. So equivalently for all vector fields xy on M, g of x comma y is simply going to be h evaluated at the image at the push forward of x and y. That means the image of x and y under the derivative map. Okay, so if F satisfies both these properties, we say it's a local isometry. Additionally, if F is a bijective map, i.e. F is a diffeomorphism, is a global diffeomorphism, then we say that F is an isometry. Okay, right, and then two manifolds are said to be isometric, two Riemannian manifolds. So we say that is congruent or isometric to NH if there exists an isometry. Okay, and an elementary sort of remark is that this is an equivalence relation. So the point is that as far as Riemannian geometry is concerned, I mean two isometric manifolds are essentially indistinguishable, right. So again this is we see this all over math. So for instance when we study group theory, if there is an isomorphism between two groups, then as far as group theory is concerned, these two groups are actually indistinguishable, right. So similarly in topology, if there is a homeomorphism between two topological spaces, then they are indistinguishable from the point of view of topology. So similarly from the point of view of Riemannian geometry, two Riemannian manifolds are indistinguishable if there is an isometry between them, if they are isometric, okay. Alright, so then we have the following proposition. That all these three manifolds that I wrote down at the start of today's lecture and that I described at the end of the previous lecture, they are all isometric. Okay. So the proof, it turns out, is quite tedious. The calculations are quite tedious, even in dimension 2 for instance. So what I am going to do instead is that I am just going to outline the proof. Okay, so I will describe what these isometries are, but then to actually check that they are isometries, you need to compare the pullback metric and see if it's the same Riemannian metric, and that involves a tedious calculation. So I won't, in the interest of time, I won't describe that calculation completely, but let me just outline what the proof is. So the first part, I am going to give a map phi from the hyperboloid to this open unit ball, which turns out to be an isometry. And in the second part, I am going to give a map which goes from the open unit ball to the upper half space, which also turns out to be an isometry between these two Riemannian manifolds. Okay. So let me first describe this map phi from the hyperboloid to the open unit ball. So instead of going to the open unit ball, I will first describe this map into Rn, and then it will be an easy calculation to show that the image actually lies inside the open unit ball. Okay. So let me first describe geometrically what this map looks like. So let me draw a picture of the hyperboloid. So remember, the hyperboloid was something like this, where this was what we call the pole, which has coordinates 0, 0, 0, except the last component is r, and then corresponding to this, if we reflect this point across the Rn plane, so this is the Rn plane, and recall this direction is the n plus first direction. Then if we reflect this point P across the Rn plane, you would get a mirror image here, which we call P hat or P dual. So this is basically just the point whose components are 0, 0, 0, etc. The last component is minus r. Now suppose you are given any point V here, any point A here, let us say. The map is the following: you join A to this dual P by a straight line. So that straight line is going to intersect the Rn plane at some point. So you call this point as phi of A. Okay. Similarly, again, if you take a point here, you again connected by a straight line that's going to intersect the Rn plane at some other point. So it's, let's say this is the point B, so you get phi of B, and so on, right. So this gives you a map from the hyperboloid to Rn. So let's write down a formula for this map. So by elementary geometry, one can check that phi of A, so maybe let me write down the components. So let us say your point A has the components A1 to An plus 1. This map is given precisely by R divided by An plus 1 plus R times A1 up to An. Okay. So now because A lies on the hyperboloid, we know that Q of A is minus R squared. So you can now calculate the Euclidean norm of this of the image phi of A, Euclidean norm squared. So clearly that's going to be R squared by An plus 1 plus R whole squared times the summation of Ai squared, I going from 1 to n. Okay, but what is Q of A? That's precisely this quantity, summation I going from 1 to n Ai squared minus An plus 1 squared, and that's equal to minus R squared. So if you plug that back in, this implies that the norm of phi A squared is R squared by An plus 1 plus R squared times An plus 1 squared minus R squared. So now just use your A squared minus B squared formula, and this will give you An plus 1 minus R divided by An plus 1 plus R. Okay, so in particular, because An plus 1 is positive, we are only looking at the hyperboloid that lies above the Rn plane. This implies that this quantity is always strictly less than R squared, because the fraction here is going to be strictly less than 1. Okay. So this implies that phi is actually a map from the hyperboloid into the open ball in Rn of radius r. Okay, so now we have a map. One has to check, and in fact one can explicitly, from the geometric picture it's clear that this is going to be a diffeomorphism, but one has to check this explicitly, that phi is a diffeomorphism, and moreover for all tangent vectors to the hyperboloid in for all tangent vectors to the hyperboloid, one has to check that if you look at the image under the derivative map and compute the norm squared with respect to the metric, the Poincare ball metric, then that is precisely Q of V, this quadratic form evaluated at V. Okay. But this quadratic form evaluated at V is precisely the norm of V squared with respect to the hyperbolic metric. Okay. So this part here is a easy but very tedious long calculation. Okay. so I'm not going to do it completely, but I would really advise you that you should try it for at least n equals 3. So maybe let me write it on the next page. So the proof of this identity which remember was just the norm v squared in the hyperbolic metric, is a long tedious calculation but I would highly recommend it in at least low dimensions. So say at least for n equals 2, I would really recommend any sort of student to really try to work this out, because I mean sort of often repeated truth in mathematics is that you cannot learn mathematics by just listening to lectures. You have to at some point do calculations, right? So doing calculations and getting the right answer is sort of equally important even in research mathematics, right? So so I would really suggest for any sort of serious student of this course to try to do this calculation at least for n equals 2. Okay, so it means you have a hyperboloid lying inside R3 and you do this projection to get a map into the disk of radius r in R2, and then you try to prove this identity. So I would highly recommend this exercise. Okay, so now let me describe a map which goes from the open unit ball into the upper half space. Okay, so this is the following map explicitly. So psi of x1 up to xn is given by 2 times x1 by d, 2 times x2 by d, etc., 2 times xn minus 1 by d, and the so let me write this slightly smaller so that I can fit so up to the first n minus 1 coordinates, it's just 2xi divided by d, and the last coordinate is r squared minus the norm x squared by d, where what is d? So d is just the quantity x1 squared etc. up to xn minus 1 squared plus r minus xn squared. Okay. So the easy part is that psi of any x lies in the upper half space if x lies in the unit ball, right? Why? Because if x lies in the open ball of radius r, because then this numerator is positive. So the final coordinate is positive, so it lies in the upper half space. And then again one can check the following, that psi is a diffeo. So in fact one can explicitly write down the inverse, and again that if you take the derivative map and calculate the norm squared of any tangent vector after you apply the derivative map, so this is the norm squared in the upper half space, that is going to be the same as the norm squared okay. So again, so this is the isometry condition. So again this is long calculation but highly recommended. At least when n is 2, okay. Alright, so maybe let me make a sort of small remark that when n is 2, this map to psi that I introduced in the previous slide, that's actually a very familiar map. So if you identify R2 with the complex plane, so the point xy is identified to the complex number z equals x plus iy, then this map psi in these complex coordinates is precisely given by a Mobius transformation. Okay, and this is actually a familiar Mobius transformation. This is simply the Cayley transform. So psi in this case the ball of radius r is basically just the disk of radius r in C, and the upper half space is simply the set of all complex numbers w whose imaginary part is positive, okay. So this psi is essentially a Mobius transformation that that takes a point in the disk of radius r to the upper half space, and this is simply the Cayley transform. So psi is in fact a biholomorphism. So this is something that we study in any sort of basic course in complex analysis, that a disk, an open disk, say a unit disk, is biholomorphic to the upper half plane, right, and the biholomorphism is given by something called as the Cayley transform, and this is precisely the Cayley transform. So the map psi that I wrote down is actually a generalization to n dimensions of this basic Cayley transform that we learn about in any course in complex analysis. Any course in complex analysis that talks about conformal transformations always mentions this Cayley transform, okay. So there's this very nice connection in dimension 2 between the Riemannian geometry of the Poincare ball and the Poincare upper half with complex analysis. Alright, so the next thing I want to talk about are self isometries. So that gives rise to what is called as the isometry group, okay. So for any Riemannian manifold Mng, we define the isometry group of Mg to basically be the set of isometries from Mg to itself. Okay, so clearly this forms a group under composition. Okay, that's easy to check. Then for all points P in M, we also consider the isotropy group or the stabilizer of the isometry group. So this is basically the set of all isometries that fix this given point P. Okay, so of course it's not necessary that given a point P there will be an isometry that fixes that point P other than just the identity, the trivial isometry. So it's in general this isotropy group. So this is called the isotropy group. This is called the isotropy group at P. So in general that could just consist of the identity element, right? But in general it might also be some larger subgroup of the isometry group. So then the most fundamental theorem about these isometry groups is the classical theorem called the Mayer-Steenrod theorem from I think the 1930s, if I'm not 1930s or 1940s. So this says that if Mg is a Riemannian manifold, then the isometry group is a Lie group where the topology on the isometry group is the so called compact open topology. Okay. So this is basically the topology of uniform convergence on compact sets. So with this topology the isometry group, it turns out, has a nice smooth structure and it becomes a Lie group. We won't prove this because the proof requires some effort, but I thought that this is such a basic fact that you should at least be aware of it. So instead let me also state a nice theorem on the isometry groups of some standard Riemannian manifolds. So these are the so called model spaces. So isometries of model spaces. So what are the model spaces? They are basically the Euclidean space, the sphere and the hyperbolic space. Okay, the reason why they are called models will be clear only much later in the course. In fact, these three are going to serve as models for sort of zero curvature, which is the Euclidean space, positive curvature, which is the sphere, and negative curvature, which is the hyperbolic metric. Okay, but this part will be clear only later in the course. For now, we will just call these three examples as our model Riemannian manifolds, and part of the reason they are called model is because they have some, they have some very nice properties. One of the nice properties will be clear from the statement of this theorem. Okay, so the isometry group of the Euclidean space. So we obviously know some basic isometries of the Euclidean space. So obviously if you take a rotation or a linear transformation with an orthogonal matrix, then that clearly preserves the inner product on Rn, in fact by definition. Similarly, one can take translations in Rn that will also clearly preserve the inner product, right. So it turns out in some precise sense these are the only isometries of Rn. So in fact the isometry group is a semi-direct product of these two. Okay, so these represent the rotations or the orthogonal transformations which preserve the origin, which keep the origin as fixed, and these are the translations. Okay, and then one can also, for any given point P, one can also write down what the isotropy group is. So if you are fixing the point P, might as well take P to be the origin, then clearly the isometry group that fixes that is simply the rotations. Okay, so now coming to the sphere, the isometry group, the sphere is contained inside, the sphere of dimension n is contained inside Rn plus 1, and then clearly if you have an orthogonal transformation in Rn plus 1, that's going to preserve the sphere of any fixed radius, and it's clear that it's also going to preserve the induced inner product on the sphere. So clearly this is On plus 1. Okay, so just to sort of draw a picture, so clearly the rotations, I have drawn the picture in R3, the rotations in R3 preserve the sphere and preserve the inner product. What about the isotropy group? If you fix a point P, so in this picture, suppose I look at the isotropy group of the north pole, then it's clear that at the equator you have a lower dimensional sphere, right? So at the equator here, sorry. So at the equator you basically have this lower dimensional sphere, and it's clear that if you take an isometry of this lower dimensional sphere, then that's going to be an isotropy of the north pole, right? So in other words, this is given by On. Alright, and what about the hyperbolic space? So let me, I think, shift back to red. I don't know why the color changed midway. So if you take the isometry group of the hyperbolic space, then it turns out that it's going to be this group that's called SO plus n comma 1. So these are the set of all, so again the hyperboloid lives inside Rn plus 1. So these are the set of all linear transformations in Rn plus 1 which preserve this form eta, where eta is the quadratic form with diagonal 1 1 etc., except in the last component you have a minus 1. So this is basically let me here, since I already have a notation for this, so this is the so these are all the n plus 1 invertible matrices which preserve this quadratic form Q, and I also want the determinant of this linear transformation to be 1. Okay, and T maps the positive the space where xn plus 1 is positive into xn plus 1 is positive. Okay, so this is the full description of this group SO plus of n comma 1. So it turns out that the isometry group, not surprisingly, is given by this group. And now if you again take the isotropy group, it again turns out to be On. So I'll maybe just explain with this picture. So you have the hyperboloid here. So let's say I want to calculate the isotropy group of this pole. Then the idea is that if you simply take the rotations in this Rn that's sitting inside Rn plus 1, then that's actually going to preserve the quadratic form Q, and it's going to keep this point P fixed, right? So you just take the rotations here, right? So that is going to preserve P, and that's going to be an isometry of the hyperbolic metric. So that is why and of course rotations in Rn is basically just given by On, right? Alright, so let me finish by the following observation. So, remark, in each of the three cases above, we see that the isometry group acts on M transitively. So, here Mg is one of these three model spaces. So, we see that the isometry group acts transitively, and if you look at the isotropy group at a point, then the isotropy group will act on the tangent space via the derivative, and by some effort one can also check that the action of the isotropy group on the tangent space is also transitive. So, Riemannian manifolds with this property are called homogeneous, where the isometry group acts transitively, and the Riemannian manifolds of the type where the isotropy group acts transitively for all points P, they are called isotropic manifolds. Okay. So, it is a fact that in fact if a Riemannian manifold is isotropic, then it will also be homogeneous, but the converse is not true. There are examples of homogeneous manifolds that are actually not isotropic. So, these model spaces are very nice in the sense that they are homogeneous and isotropic. So, homogeneous in some sense means that that Mg looks the same at all points. Okay. On the other hand, isotropic means that Mg also looks the same in all directions, because the action on the tangent space is transitive. Okay. So, these model spaces are special in the sense that that they are extremely symmetric. They look the same no matter from where you look at and no matter in what direction you look at, right. All right. So, that is it for this lecture. So in the next lecture I will describe another very important example, namely that of a flat torus, right. So I will use some of this discussion of isometries to talk about the sort of flat metric on a torus. So, that is it for today. Thank you for your attention, and I will see you in the next lecture.